Okay, hi everyone. Welcome back to part 2 of lecture 20. And now we're going to see proofs and how they relate to hardness of approximation. All right, so, if you remember again from your algorithms or complexity course, right? So the goal of complexity theory is to characterize mathematical problems is to classify the mathematical problems into how long it would take for algorithms to solve those problems, right? So that's what we're trying to do in complexity theory. We're trying to classify the problems based on their difficulty, the amount of resources that we need, right? And we saw that, well, there's the famous classes that you have seen, which is NP, right? And what is NP? It's the set of languages, right, such that there exists a polytime Turing machine V, right, which is a verifier. So there is a polynomial time verifier such that we know that X is in the language, right, is a yes in instance, if there exists a witness, and this witness, so this is called usually witness or proof, okay, so witness or proof, right? And what is the characteristic of this witness and proof? Well, it's a small, right? So this is the characteristic, is a small. There's a small witness or a small proof such that, oh, this should be W here, sorry. Like VXW is equal to 1, right? So the verifier, it's just a set of classes for which there's a short proof, and there's also a verifier that this verifier, for any input in the instance, there exists a proof which is short, such that when you give the instance and the proof, the verifier can verify that this is indeed in the language, right? So this verifier tells you is an automatic procedure, is an algorithm that verifies that X is the input given the proof, right? So that's the if and only if, right? So if X is not in the language, then there's no short proof on which the verifier will accept, right? That's why we have the if and only if here. Does that make sense? Okay, so this is our familiar definition of NP, right? And the idea here is that, NP is kind of the language for which it tries to encapsulate your creativity, right? Because let's say, is the problem is that if you didn't know the solution, they can possibly be very hard, right? But if someone gives you the solution, you can quickly verify that that solution is correct, right? So this is why NP is philosophically so important, right? Because it captures essentially what can be talked about in scientific process, right? Because you're not going to read a paper that is exponentially long on the size of the claim, right? So you'll never, or, whenever someone's asking you to explain something, if you're going to say, oh, my explanation is so long that it will take us 200 years to explain, you're like, okay, then we don't have time. So, right, it's a little bit of futile. Okay, so, all right. And now we also have, the class BPP. And this class BPP is the class which is bounded probabilistic polynomial time. And this is the class that encompasses randomized algorithms. Okay, so randomized algorithms are roughly here. Okay, there are other classes, like more refined classes, but this is kind of the canonical class for randomized algorithms, right? So let me put here like randomized algorithms. And what is this class? So this is the set of languages again, right? Like language is just a subset of all the inputs, such that there exists a polytime Turing machine M, right? Such that for every X, for every input X, we have that if you give me a random string, so this is R is uniformly a random here. If I take a random string that is small, right, like poly size and uniformly random, and I give this random string to my Turing machine M, okay, this Turing machine Mx will be equal to L of X. So what is L of X? L of X is the function that's equal to 1 if X is in the language and 0 otherwise. Okay, so this is just a shortcut to say, like, L of X is in the language or not in the language, right? So the idea is that if you remember, like a polynomial time Turing machine, a Turing machine is a deterministic procedure. So how do you make Turing machines kind of encapsulate randomized algorithms? All you say is, oh, this machine will take your input and will also take some random bits, right? Like, and then once it has the random bits, then it operates deterministically, which is essentially saying at every time that it needs to flip a coin, it just looks at one bit of the random, like of the random string you have, right? So this is how we encode a randomized algorithms, right? So this is a randomized algorithm. Right? And here, what is this saying? It's saying that for most random strings, your algorithm, like this Turing machine M, will output the correct answer, right? So that's what BPP is saying. Like for most choices of random strings, M will output right answer. Right? So that's the complexity class that characterizes randomized algorithms. But here's a specialization of BPP, okay, which is just called like randomized polynomial time algorithms, right? So, and here is a set of languages, okay, such that there exists a polytime Turing machine, such that if X is in the language, then with high probability, with probability 2/3, I'm going to output that X is in the language, right? And if X is not in the language, then I demand that you never output that X was in the language. Does that make sense? So, okay, and you might ask, well, I mean, but BPP is kind of, you know, a more relaxed version and it encompasses randomized. Why would we want RP? Well, it's because sometimes natural problems are in RP or in co-RP, okay? So, and for example, if you look at the PIT problem that we talked about in class, the polynomial identity testing problem, okay? The polynomial identity testing is in co-RP, okay? And it's in co-RP just because we're asking if a polynomial is 0, right? But let's just ask, suppose that we ask like the co-PIT question. What is the co-PIT question? Is given a circuit or a device computing a polynomial P, right? Is P different from 0? Right? So why is this question in RP? Well, because what happens if P, remember, if P is not the 0 polynomial, so P would be in the language, then we know that evaluating at a random point with high probability gives us that P will give us a non-zero evaluation. So we know that P is non-zero, right? But now, what if the polynomial was 0 to begin with, right? So this device that computes the polynomial was computing the 0 polynomial. Then we can say that with probability 0, we're going to output that this device is computing a non-zero polynomial. Does that make sense? Because every time we evaluate, we're going to get 0 back. So then we can just say, okay, this is the 0 polynomial, right? Does that make sense? So, okay. So these are some complexity classes, right? And again, yeah, so co-RP is, they're the languages such that their complement is in RP, right? So that's what we did with PIT, right? So the complement of PIT is in RP. So, all right. So, all right, yeah. So then we can see like, okay, so we know a bunch of problems in complexity classes as we discussed, right? So, well, for example, we know that matching, like the matching problems are definitely in P. We know the Hamiltonian cycle is in NP, right? And why is the Hamiltonian cycle in NP, right? So the idea is, suppose that I gave you a graph G. Let's just verify that this problem is in NP, right? So I give you a graph G VE. Why is the Hamiltonian cycle in NP? Well, if this graph has a Hamiltonian cycle, what is the witness that we would give for the Hamiltonian cycle? Well, this is the input, and the witness would just be the cycle. Cycle C. This is our witness or proof. And now, what is the algorithm that checks? Well, the algorithm will just do what? The algorithm will just say, okay, my algorithm M, my algorithm V, the verifier, will take my input and my witness and will do what? Well, checks that C is a valid cycle. Correct? And well, once I have a cycle, how long does it take to check that's a valid cycle? Well, one, we need to check that it's a cycle that doesn't repeat any vertices, right? And it passes through all the vertices. So I can just follow the cycle and I can check were all my vertices there and did I repeat any vertex? And right, if those answers are correct, then we know that it's a Hamiltonian cycle. Does that make sense? Okay. Great. And the same thing is for clique and all the other problems, right? So, and we already saw the PIT is in CoRP. So these are some examples. And all right. And now let's talk about how we can go from complexity classes to proof systems, right? Because now what did we see? We saw that NP is a complexity class that has some sort of proof, right? Like I have my input and, you know, like NP, you can think is the set of languages that have a verifier, such that if you give a proof, you say, oh, this is my input, and this is a proof that my input is in the language. So this verifier will accept, right? But if my problem is not in the language, then no proof can fool my verifier, right? My verifier is foolproof. All right, so proof system looks like this, right? So we have a prover and a verifier, and they will agree on the following. Okay, the prover must provide proofs in a certain format. And the verifier can use algorithms from a certain complexity class to verify, right? So if we're talking about like NP, for example, as a proof system, NP will have a prover. We didn't talk about the prover itself, right? But we just talked that someone will give me a proof, right? But you can think that there's a prover that must give proofs of polynomial size. Polynomial size on the size of the input, right? So given an input, the prover must provide proofs of polynomial size. And the verifier, what is the verifier doing here? The verifier is using algorithms from P, from the complexity class P, right? We're just using a deterministic polynomial time algorithm, right? That's what we did for NP, yeah? So you can see NP as a proof system, right? And now a statement will be given both to prover and verifier. So for example, the graph G, this graph G has a Hamiltonian cycle, right? So this is the statement. And now a prover, you know, the prover wants to show off. The prover is like, oh, you know, like, I know how to prove this, you know, and the verifier is like, I don't believe you. I don't think you can solve it, right? But I can certainly check if your solution will be correct. So then what does the prover do? The prover will write down a proof of the statement. And now the prover will send this proof to the verifier. And then the verifier can use this algorithm to check the statement and proof and accept and reject accordingly, like what we did in Hamiltonian cycle, right? So what would be the proof that the verifier could demand? The verifier can just say, if you can prove it, just give me a Hamiltonian cycle, right? And then you can check. Does that make sense? Okay. So then, again, just as we defined, right? So L is in the language, right? And then the verifier can use any polynomial time Turing machine. And given an element X, the prover needs to give you a proof of polynomial size. That's all. This is the requirement. And then you can see NP as a proof system. Right? All right. So yeah, so this is what we're doing, right? So because the verifier, the verifier will pick an algorithm like beforehand, right? So it picks one algorithm that has to work for all inputs, right? All right. So, okay, yeah, so this is what we discussed already. So I'm just gonna skip the slide. And now the thing is, every time that you create a proof system, right? We have two things to say, how good is your proof system, right? Because there could be a proof system that's kind of trivial, like you never check the proof that's given to you. So then what good is this proof system? It's not very good, right? Because it's kind of useless. Like we don't need to use it if you're going to accept anything, right? So how good is the proof system? Well, we need two parameters aside from efficiency, right? One is, well, we need to be able to make a decision within our lifetimes, right? So then efficiency is certainly one parameter, but there's other two parameters, and these are completeness and soundness, right? So we say that a proof system is complete if correct statements have a proof in the system, right? So if a statement is correct, we must be able to find a proof in the system, right? And why is this good? Well, it's because if we have a complete proof system, then it means that we can verify any claim that we would like in this system, right? So this makes sure that this system is very useful, right? But now the problem is, well, the system has to also be sound. And why is that? Well, we want to be able to check fake news, right? If someone sends you fake news, you want to be able to verify that it's fake, right? So, and what does it mean? It means that false statements do not have a proof in the system. Nobody can give you a false statement and the proof that will convince you, right? This would be great because, you know, we can always spot what it's wrong, right? Does that make sense? So those two are very desirable characteristics of a proof system, right? If it's correct, we can prove it. And if it's false, no one can prove it, right? There's no proof. All right. So again, if we have NP as a proof system, we know that NP is complete, right? Because if X is in the language, which means that it's a correct statement, right? By definition, we know that there will be a witness of polynomial size such that the verifier will accept. And is NP soundness? It's sound. It is also sound because we know by definition of NP that there only exists a witness if and only if X is in the language. So if X is not in the language, we know that for any witness, the verifier will reject. Does that make sense? So, okay, and, well, you know, this is great that we have this proof system, right? So, okay, but certainly the question here is, well, if a problem is in NP, we would like to solve it because we don't have the prover, like oftentimes we don't have a prover to give us a proof, right? So, all right, but proof systems, they can also be used for different things, not just for complexity classes, but in other interactive proofs. So for example, even in cloud computing and all these kinds of things, like you can have, when you delegate computation, for example, this is what is known, you will use proof systems to model interaction with the cloud, for example. Okay, but anyways, so so here, now here's the thing, NP is great as a proof system, right? But it allows only us to use like a deterministic algorithm. Now, what if we allow the verifier to run a randomized algorithm? Still polynomial time, but a randomized polynomial time algorithm, right? So, and this is what we call a probabilistic proof system, okay? So in a probabilistic proof system, the verifier has now a randomized algorithm V, for which, given the language L, which is the language of correct statements, X is in the language, then there exists a proof. And here we're not talking about size yet, okay? Like just there exists a proof such that V, the verifier, when it gets X as an input, okay? So I'm not talking about the length, and notice that I'm not also writing VXW, because now what I'm going to do is I'm going to constrain my verifier a little bit, that my verifier is not, sometimes is not going to be able to see the whole proof. It's just going to be able to look at the proof as an oracle, So when we say that V will look at W as an oracle, it can query the proof. Okay, then we write like this: V has input X, but it uses W as an oracle. So we can only access it through oracle calls. And what do I mean by oracle calls? I mean that the randomized algorithm can say, oh, I'm going to flip a coin and decide on a random bit of the proof to look at. Does that make sense? And then I can say, oh, can you give me the 10th bit of the proof? And then it may need more bits. Okay, give me the 11th, give me the 20th. Does that make sense? So we'll query a couple of bits from the proof. Okay, so a probabilistic proof system is this randomized algorithm that if X is in the language, there is a proof such that this randomized algorithm, okay, will always accept my input given the proof, okay? And if X is not in the language, then for any proof W, we have that the probability that V accepts a wrong proof, right, because X is not in the language, is less than or equal to half. Does that make sense? So we have a gap here, right? So if X is in the language, there is a proof such that my verifier, even though it's randomized, will always accept. But if X is not in the language, more than half of the proofs are bogus. Or sorry, for any proof, right? For my algorithm, for half of the time, will output that this proof is bogus, right? We'll be able to catch it, right? We catch it with high probability. Does that make sense? Okay. So now, what is the definition of probabilistic checkable proofs, right? So this is a probabilistic proof system. And now we're going to give it the definition of probabilistic checkable proofs. So the class of probabilistic checkable proofs, okay, is a class of languages, right? Just like NP is a class of languages, right? So it consists of languages that have a randomized polynomial time verifier such that, here's the thing, oops. So if X is in L, then there exists a proof W such that this probability is 1. And if X is not in the language, for any proof, we can catch it with high probability. Okay, so this is the class. So now this is the complexity class of languages, right? So we're now, again, doing the same thing that we did for NP or BPP or so on, right? We're saying, okay, there are languages, and these languages, they are in the class of languages of probabilistic checkable proofs if there is such a verifier. Does that make sense? Or there's an analogous definition from the other complexity classes. Okay, so, and now, so the definition that we just talked about, as you can see, already motivates us to define this complexity class in terms of proof systems, right? So this whole discussion that we have had so far is just to motivate how natural it is to define complexity classes in terms of these proof systems, right? So, and here is one way that we can do the class of interactive proof systems, right? So the class of interactive proof systems, which is called IP, consists of the languages L that have an interactive proof system where, okay, so the verifier V is a randomized polynomial time algorithm, and there is an honest prover P. Now, this honest prover P can be all powerful, can do whatever, like can solve uncomputable problems, can do whatever, you know, it can do. And now for any X, okay, for any input X, if X is in the language, then for the honest prover P, for an honest prover P, this honest prover will give you a proof, right? Like a proof pi of X, pi, such that now our verifier will always accept. And again, if X is not in the language, sorry, again, if X is not in the language, for any prover, now, you know, an honest prover will not give you any proof if the input is not in the language, right? But it could be that you have a trickster that's trying to fool you, right? It's trying to say, oh, hey, I know how to prove this. And you're like, well, no, you don't, but sure, we can try, right? But here, for any prover, the bogus proof will be caught with high probability. Yeah, so it's the same thing as kind of the things that we were discussing in the previous slide, okay? So, all right.
So now you're quantifying
Now,
over provers.
What is the picture that you should have in interactive proofs, right? So the picture is that we have here like the verifier, right? And there's an all-powerful prover here. So let me just write prover as a big so that you know it's like, oh, it's really powerful. And the prover is trying to convince the verifier that it can do something really hard, like solving an NP problem. So the verifier is going to do what? Oh, okay, sure, sounds good. I have an algorithm M, and on input X, what the prover must do is the prover is going to say, okay, here, I'm going to send you a proof. And then the verifier would just say, okay, I'm going to run M on X and W, right? And I'm going to send you the result, right? So I send you the result of MXW. And then we know if the proof is correct or not, right? And the idea is that for probabilistic checkable proofs, right, you're not able to fool the verifier that much. Okay, and so now, all right. Sorry, can you hear me?
Hello?
Oh, wait. Sorry, I cannot hear. Can I hear? Can you say something now?
Hello?
Oh, okay. Now my sound is working. Sorry, you're asking something?
I wanted to ask, like, now you're quantifying over provers instead of quantifying over proofs.
Yes, exactly. Here, yes. Sorry. Yes. So here we want, well, here we're still not quantifying the prover, right? We're just saying that there is an honest prover. But in cryptography, like when you talk about, you can try to constrain the prover. Does that make sense? So if you constrain the prover, usually this has applications in cryptography. So you can see that in the realm of cryptography, not here. Yeah. So, but you could. If I don't constrain the prover, I can just talk about the proof, right? Like the same way that I talked about NP without talking about a prover.
Okay. But like, how is it different if I say like there exists a proof, like instead of honest prover, if I say there exists a proof, because an honest prover will always give me a proof, right? I guess.
Exactly. In this case, yeah. In this case, yes. All I'm saying is that I'm giving you the reason why I'm giving you like these different definitions is because like if you start studying more complexity theory, you start seeing that there's a difference once you start constraining like the prover and so on, right? So because you can say, oh, if the prover would be you know, let's say any polynomial or like any polynomial time algorithm, but let's say like your V is a randomized polynomial time algorithm that runs in at most a certain amount of time, right? Or P can be a stronger complexity class, maybe even instead of P, it can be E or something, right? Like it can be some, but it cannot solve like a lot of problems, right? So the more you constrain your prover, the less the prover can do, right? So for example, if you assume the prover cannot solve NP problems, right? NP complete problem, then it's already like, but the prover could be really powerful. So, but it's much more powerful than your verifier, right? So if your verifier runs in linear time, right? Then maybe someone that runs in polynomial time, but much more than linear, like that, or they are much more efficient, like they could still kind of like interact with you, right? So there's different ways of doing this, but this is studied in different areas. That's why I'm introducing it this way, so that if you see it later in your studies, you'll be like, oh, I'm not surprised. I've seen this before, right? Okay, cool. Yeah, that's a great question. Like, why am I doing this? And I should have said, right? All right. So, all right. Now let's quantify probabilistic proof systems, right? So we talked about all these proof systems, and now we have a lot in our heads. But let's quantify this class of probabilistic checkable proofs, right? So we saw this class of probabilistic checkable proofs, and now what we want to do is to do the following. Okay, so there's all these languages that have this randomized polyverifier. But now let's say that PCP, so this class PCP of probabilistic checkable proofs, we can quantify the languages. In which sense? right? So now we're going to constrain just the proofs, right? So the class PCP of Rn and Qn consists of all the languages L which have a probabilistic checkable proof, such that on inputs X of length N, now we're going to see what those two parameters are for. Our proof, okay, so our verifier, these are constraints on the verifier. The verifier can only use big O of Rn random bits. So Rn and Qn are functions, right? They're functions of natural numbers. Like, so R is a function from the natural numbers to the natural numbers, and Q is the same. And you should think of R and N as the random bits, like the random bits that the verifier would use, and Q is the number of queries to the proof. Does that make sense? So the thing is, and here, remember, because we have an oracle, right, W, the oracle can have any size, but R and Q are functions of N, and N is the length of X, right? So N is the size of X. So what are we saying? Well, here's the idea. The verifier V will take a look at your input X and is allowed to query the proof W. This is the proof W. So V can like take X, and V has its random bits, but V can use Rn random bits, but it can only look at Q. Suppose that Q is 3. So I can only look at 3 bits of the proof, and I have to make a decision, and I have to have those 2 guarantees. Does that make sense? So this class PCP RQ, okay, consists of all languages in PCP such that the verifier must use at most Rn random bits, like or O of Rn random bits, and can only examine O of Q bits of a proof. So the proof can be of any size. Now that's the difference, right? Like, and in NP, the proof had to be small. Here, the proof can be really large, but the verifier can only query like O of Q bits of a proof. Does that make sense? Okay, so, and here's the amazing fact about the PCP, like this class. It turns out that PCP of log n, with R being log n and Q being 1, is equal to NP. Okay, so now let's unpack what this means, right? Like, and why this is kind of really amazing, right? This is saying that, so this here is saying that the class NP, remember, the class NP had like proof, it has proofs of polynomial size. That now, if the verifier is allowed to look at the input and the entire proof, it runs, it always accepts, right? Like it only accepts if the input is in the language. But here what we're saying is that, okay, X is in NP, right? Like this language is in NP, if and only if we can also have a probabilistic checkable proof, which uses log n random bits and queries my proof in constantly many entries. I only need to see constantly many bits of the proof to be able to tell with high probability if the proof is correct or not. Okay. Right, and this is really impressive, right? Because if someone gives you such a proof that is valid for PCP, you don't even need to look at the entire proof. You look at like 3 bits of the proof and you're able to tell with high probability that, yeah, this proof is correct, right? So this is kind of fantastic. And well, and now the question is, well, why did you take this whole detour to talk to me about PCP? Sure, it's amazing. It's an amazing theorem, but how does this relate to hardness of approximation? Well, it turns out that the PCP theorem is one of the major technical tools to prove hardness of approximation results. Okay, so, and let's talk about it now a little bit in the last minutes of the class, right? So how can we talk about PCP and hardness of approximation? Well, it turns out that we can use the PCP theorem, okay, to show that max 3 set is hard to approximate and is actually equivalent to the max 3 set problem being hard to approximate. Okay, and this is the content of this slide, right? So what is the max 3 set? The max 3 set problem is the following. Your input is a 3CNF formula, okay, on Boolean variables like x1 up to xn, okay, and m clauses, right? And what we want to output is the maximum number of clauses which can be simultaneously satisfied, right? So what is a 3CNF? Let's do an example here, right? So is a big end. So let's say x1 or minus x2 or x5 and x3. So it's a big end of ors, right? So x3 or minus x7 or x9 and so on, right? So, and all these clauses have 3 literals, exactly 3 literals, right? So the input here is this 3CNF formula. And what we want to output is the maximum number of clauses of the formula which can be simultaneously satisfied. Okay? So, okay, so this is the max 3 set. And here's the theorem, okay? So the PCP theorem implies that there exists an epsilon such that there is no polynomial time 1 plus epsilon approximation for max 3 set, unless P is equal to NP. Okay? And moreover, if max 3 set is hard to approximate within a factor of 1 plus epsilon, then the PCP theorem holds. Okay, so not only the PCP theorem, okay, implies hardness of approximation, is equivalent to the hardness of approximation of max 3 set. Right? So this is also the significant importance of this connection between these proof systems and like hardness of approximation, right? That they're equivalent. Okay. So, all right. So then let's just like go over the proof here in the time that we have, right? So let's assume that the PCP theorem holds, right? So, okay. So if we assume that the PCP theorem holds, let's say that, you know, L in PCP log n1 is an NP complete problem, right? We know that PCP of log n1 is equal to NP. So let's take a NP complete problem, which is in the class, right? And here, let's say that V is the O of log n Q verifier for L, where Q is a constant, right? Because that's the definition, right? So this L has this verifier. And now here's what we do. Let's do a reduction from L to max 3 set, which has a gap. And this will prove the hardness of approximation. Does that make sense? Just the same way that we did for the traveling salesman problem, right? All right. So given an instance of problem, like of problem L, right? So what we can do, we can construct the 3CNF formula phi of x with m clauses such that for some epsilon, we have that if x is in the language, then we know that phi of x is satisfiable. And if x is not in the language, then we know that no assignment satisfies more than 1 minus epsilon times m clauses, right? That's what we want to find. All right, so what do we do? Well, here's the thing. Once we take the language L and an input an input x, which is either in the language or not in the language, what do we do? Well, here's the thing. V does not have a lot of random bits, right? V uses O of log n random bits. So what do we do? Let's enumerate all possible random inputs for the verifier V, right? So the length of each random string is O of n. So what is the number of random inputs? The number of random inputs is exactly poly n, right? Because this is exactly like poly n is 2 to the O of log n, right? Like this is exactly equal to poly n. Because let's say 2 to the C log n is equal to n to the C, right? That's why. So we know we have polynomially many random strings. Now, for each random bit, V, once I give those random bits to V, V becomes a deterministic algorithm. Does that make sense? Because now I already gave the random bits to V, right? So that's what the random bits will do. Because remember, what is a randomized algorithm? A randomized algorithm is just the same thing as, well, V over X is the same thing as a deterministic Turing machine over X when I give it random bits. But if I fix the random bits that I give to V, then V is a deterministic algorithm, right? So in particular, if V, when I fix R, is a deterministic algorithm, I know which positions of the proof I will query. Does that make sense? I already know the positions of the proof. So what do? For each R, V will choose Q positions, and I know which ones they are. They'll be like I1 up to IQ of R. And these are just dependent on the random bits, right? And now from these positions, we have a Boolean function that goes from 0, 1 to the Q to 0, 1 and accepts if and only if this random function is 1 on the, when I see the Q elements of the proof. Does that make sense? That's what V is doing, right? Because a deterministic algorithm is a function from X to 0, 1, right? So in this case here, like for each random string, we know what the positions are. So then we can come up with this function f that for the random bits R that accepts if and only if when I see the proof, I can decide whether it's 0 or 1, right? Does that make sense? Okay, great. So we have this function. So this is what we did, right? So for each R, we have this function fr, which is encapsulating whether V is accepting or rejecting. And now what do? Well, we can simulate the computation fr of the verifier for different random functions, right? And witnesses W as a Boolean formula. Right? And this is the usual way on how we simulate this computation by a Boolean formula, right? This is the similar way in which you saw like the proof of NP completeness, right? So we can do the simulation as a Boolean formula, and we can do this with a CNF of size 2 to the Q. And if I convert this to a CNF, to a 3 CNF, we can get a formula of size Q times 2 to the Q. Okay, so this is the standard reduction to the CNFs, right? And now what do? Well, now let's say that this phi of X is the 3 CNF that we get by putting together all the 3 CNFs constructed above. For each R, we're putting together these 3 CNFs. Okay, so what's the size of phi of X, right? So, well, so the size of phi of X will be poly n times Q to the 2 to the Q clauses, right? So I have this many clauses. So it's okay, right? It's a poly time, because remember Q is constant. So there's polynomially many clauses, right? And now let's say if X is in the language, then we know that there's a witness W such that VXW accepts for every random string. Does that make sense? In this case, this formula that we constructed is satisfiable. Okay? And now, if X is not in the language, then what happens? What does the PCP theorem tell us? Well, it tells us that the verifier will say no for half of the random strings. Right? So now, for each such random string for which the verifier says no to half of the random strings, right? At least one of its clauses must fail. Right? One of these clauses from like, remember, for the input R, suppose that I take my random bit R for which my witness, my verifier will fail. For this R, this CNF that we constructed of size Q times 2 to the Q is not satisfiable. Right? So we know that at least 1 over 2 times Q times 2 to the Q of the clauses will fail. Right? And why is that? Because for each random string, at least one of its clauses fail. Right? So for each random string, what is the fraction of the clauses that failed? Was 1 over q times 2 to the q. Right? But we know that the verifier will say no for half of the random strings. So then what is the total fraction of random strings? Well, it's 1/2, which is the fraction of random strings that fails. And for which one that fails, we have 1 over this fraction of clauses that are failing, at least, right? So we know that at least this many clauses fails. So we can take epsilon to be 1 over 2 times q times 2 to the q, which is a constant. Does that make sense? So this is the proof outline, right? So we just have to fill in the blanks on how to do like these two things here, but these are pretty standard. So you can do this as an exercise, or we can do this in the office hours, yeah? So, all right. And, okay, well, due to the time, let me not digest the proof, but okay. So to conclude, what did we learn today, right? So we learned today that it's important to study the hardness of approximations of NP hard problems, right? And that different hard problems have different approximation parameters. Like, for example, we saw the general TSP problem, and we also saw this 1 plus epsilon hardness for max 3 set. And we also saw the max cut has an upper bound on its approximation, right? So we definitely know that different problems have different approximation parameters. And we also learned that to obtain hardness of approximation results, we need more robust reductions between combinatorial problems, right? We need to reduce problems to yes instances and very much no instances. And in particular, we also saw that probabilistic checkable proofs, they allow us to get such strong reductions. Not only do they allow us to get strong reductions, but they're equivalent to these reductions existing, right? And well, some things that we're not going to be able to see in this course, but if you're curious, you should definitely check it out, is that there's many more applications of probabilistic checkable proofs in computer science and in industry, right? So for example, in software engineering, probabilistic checkable proofs can be used for program checking, right? Because you want to verify if a software will work for all your inputs, but you cannot test on all the inputs, right? So having this probabilistic checkable proofs is good. For example, it's being used today for zero knowledge proofs in cryptocurrencies, and also in games and in other transactions, and many more applications. Okay, so if you want to venture in, you want to learn more about it, I'm happy to talk about it after class. And all right, and this lecture, if you want to know more, it's based largely on sections 1 to 3 of Luca's survey, and you can click the link to find it out, and also on chapter 7, mod 1 in Raugavan. Okay, so and these are some of the papers that I refer to here. So do you have any questions?